A 3-meter ladder stands against a high wall. The foot of the ladder moves outward at a constant speed of 0.1 meter per second. When the foot is 1 meter from the wall, how fast is the top of the ladder falling? What about when the foot is 2 meters from the wall? Now, this is the related rate problems with some sort of geometric shape, so we should draw a diagram. First, we were told that a ladder stands against the wall. And so this is the wall, this is the ladder, and this ladder is 3 meters long. Notice that the 3 meters is fixed, regardless of where the ladder is sliding toward to. The ladder stays 3 meters, but notice that the distance from the foot of the ladder to the wall is increasing, and so this x is going up. X is the distance from the foot of the ladder to the wall, and it is a variable because it keeps changing. Similarly, the top of the ladder is falling, so the distance y from the ground to the top of the ladder is decreasing. This is a variable as well. And so by looking at this, we see that there is a relationship between x, y, and the ladder, and that relationship is the right triangle. Specifically, this is the Pythagorean theorem. X squared plus y squared equals 3 squared. Technically, we should write x squared plus y squared plus z squared, but we know that the ladder is fixed, so we can just simply use 3 instead of using a variable for the ladder. X is the distance from the foot of the ladder to the wall, and so the rate at which it is changing is dx dt. This is how fast the ladder is moving, and so dx dt is 0.1, and it is as a constant rate. We were told that it is moving outward. The reason why dx dt is positive because the x is getting larger, and so the rate is increasing. We were asked to find the rate at which the top of the ladder is falling, and so this is dy dt that we're looking for. By looking at this equation, we need to introduce dx dt and dy dt. To do that, we simply differentiate both sides implicitly with respect to t. Not x, not y, but with respect to t. d dt of x squared is 2x dx dt plus d dt of y squared is 2y dy dt implicitly. And don't forget to differentiate the right hand side as well. d dt of 9 is 0. We're looking for dy dt, and so we will isolate dy dt, but first we isolate 2y dy dt, which is minus 2x dx dt. And so dy dt is negative x over y dx dt. Don't plug in any numbers yet until we get the rate of change symbolically. And now dy dt is what we're looking for at the moment when the ladder is 1 meter from the wall. What that means is that we need x equals 1 to plug it in. We also need to know what y is as well, because on the right hand side we have negative x over y dx dt. Negative x, we know that it is 1, and then y we don't know yet, but dx dt we know that it is constant 0.1. So how do we find y? Remember that this is a right triangle, and so we still use the Pythagorean theorem. If the foot of the ladder is 1 meter from the wall, so x equals 1, the ladder is always going to be 3. And so y is y. And so what is y? Y in this case, in this particular case, is 3 squared minus 1 squared, square root. No need to take the negative value because this is the dimension. And so we end up with the square root of 8. 3 squared is 9. 9 minus 1 is 8. And this is 2 root 2. And so the y that we need in this expression is therefore 2 root 2. If we plug this into a calculator, we will get negative 0.035, and the unit is meter per second because this is the rate at which the top of the ladder is falling. Similarly, if we want to find the rate as with the ladder is falling, the moment when the ladder is 2 meters from the wall, we would do the same thing and find out what the y value is when x is 2. The ladder is still 3. And so in this particular case, y is the square root of 3 squared minus 2 squared, which is the square root of 9 minus 4, or the square root of 5. And so when the ladder is 2 meters from the wall, the foot of the ladder, and when the top of the ladder is root 5 from the ground, the rate at which the ladder is sliding outward is still 0.1. Put this in the calculator, we will see that this is negative 0.089, and the unit is still meter per second. Now, as the foot of the ladder moves out, the x value increases and the y value decreases. And so if we were to look at the dy dt expression on the right hand side, that is negative x over y dx dt, we see that if dx dt is constant, this rate, if it is constant, then the magnitude of dy dt increases at the foot of the ladder, gets further out, meaning at x increases, y decreases, therefore the magnitude of dy dt increases as well. What it means is that if the foot of the ladder gets further out, the top falls faster and faster.